Hi.
I want to make sure I pronounce your name correctly.
Arum Yoon.
Arum.
Arum.
Arum Yoon. Okay, got it. Thank you. Okay, everyone, we're gonna get started with the group presentations at this time. Let's see if there's. All right, I think we have everyone in. Okay, so we're gonna get started with the group project presentations, not project, but the group leader presentations at this time. So first up, we have Arum Yoon from the Department of Bioengineering at Hanyang University. And she'll be talking about nano or cell carrier mediates efficient systemic delivery of oncolytic adenovirus for cancer treatment. So take it away. Do you have the mic on you?
Yep.
Yep.
Okay, thank you for the introduction. And yeah, first of all, I would like to appreciate all the organizer for shaping this wonderful workshop and giving me a chance to present my current research here today. So I'm Arum Yoon from Hanyang University, Seoul, South Korea. And my research is mainly focused on the development of oncolytic virus for cancer treatments. So originally, today I was talking about the systemic delivery of oncolytic virus, as in the title, but to enhance the discussion in the group meeting, so I will briefly add more about the combination of oncolytic virus with immune checkpoint inhibitor. So let me give you brief the introduction what the oncolytic virus is. Through the genetic engineering, the oncolytic virus does not replicate in the normal cell, and thus it does not kill the normal cell. However, in the cancer cell, it can selectively replicate in these cells and kill these cells. And the progeny virus from the cancer cells again impact the neighboring cancer cells so that it can maximize its therapeutic efficacy and the safety profile. Further, the oncolytic virus armed with the potential therapeutic gene can highly express its therapeutic gene in cancer cell specific mode. It can reduce the adverse side effect in non-targeted cells. Another great advantage of oncolytic virus is the tumor-specific immune response. Oncolysis-mediated tumor lysate can be the tumor-associated antigen, and this TAA can enhance the activation of immune system, which can recognize and attack the cancer cells. In these days, the immune checkpoint inhibitor is getting a lot of attention for the cancer treatment. However, as a standalone treatment, it works only 20 to 30% of people. So the combination therapy is actively exploring, and due to the immuno-oncology attribute of oncolytic virus works very well with the immune checkpoint inhibitor. So most of big pharma is seeking oncolytic virus to supplement their existing pipeline, and the oncolytic virus are high value added in combination treatment with existing immune therapeutics. So up to now, about 39 of gene therapeutics are commercialized, and 3 of them are oncolytic virus product. And the measles virus, adenovirus, herpes simplex virus, and reovirus are most used for the oncolytic viral vector, and the oncolytic virus is most frequently used for the viral vector in the clinic. The CG oncology in USA has been conducted phase 3 clinical trial with the CG0070, which is the oncolytic adenovirus, and now the company is listing in the NASDAQ. However, all those oncolytic adenovirus is first or second generation of oncolytic virus, and it can still possess the medical unmet need, which need to be overcome. So our lab has been studied developed the oncolytic virus for about 20 years, and with over 200 publications, we have in-depth understanding of oncolytic virus, and also found 7 ways to improve the oncolytic virus ability throughout the direct cancer cell lysis, inhibition of angiogenesis, potent induction of anti-tumor immune response, and targeting the multiple oncogenic pathway, and overcome hostile tumor microenvironment, and enhancement of synergistic effect in combination treatment. On top of those things, we have also established nano-complex platform which can enhance the systemic delivery of oncolytic adenovirus. So I have been very fortunate to meet the Professor Peter Kim throughout my supervisor, Professor Yoon, and Peter offered us many opportunities to collaborate with many mathematicians, and we have through them collaboration, we have published 7 papers last 10 years. And even though I don't really understand the equation and the formulation about the in the papers, but I get the we get kind of sense of quantitatively understanding of virus infection and immune response against the virus. It also helps us to pinpoint the factors for treatment success or failure, and we can also fine-tune the therapeutic strategy and design new. So perhaps you can share the presentation. Yeah. So these are all the about the oncolytic adenovirus infection and and the immune response against the virus, and we also the systemic delivery of virus, and so I hope we can continue. I look forward to continuing the collaboration through this meeting. So in this regard, I would suggest possible question for the mathematical modeling, and I will also provide some related data for my presentation. This is a part 1 about the systemic delivery of oncolytic virus. So despite of many advantages of oncolytic virus, when the virus is systemically delivered, the therapeutic efficacy is not sufficient due to its natural tropism. When the virus systemically delivered, virus directly goes to the liver, which can lead to hepatotoxicity. And the virus is kind of immunogenic. It can induce the strong immune response against the virus. Furthermore, the virus can stick to the serum protein or the blood factors. It can induce the short blood circulation time. With all of these phenomena, virus can not be accumulated the target tumor tissue, which can reduce the therapeutic efficacy. Due to these reasons, most of oncolytic virus clinical trial choose the local injection as an injection route rather than the systemic injection. To overcome these limitations, I conjugated the EGFR targeted antibody Erbitux into pegylated PAMAM nanoparticle, which is PPE, and this the positively charged PPE is conjugated, complexed with the negatively charged oncolytic virus, generating PPE oncolytic adenovirus complex. And this oncolytic virus can be injected the patient who has the metastatic nodule. So after blood circulation time, the complex can encounter the EGFR high expressing cells, and through the specific interaction of EGFR and the orbitux, it can internalize to the cancer cells. And after internalization, the virus can be released from this complex, and then virus can act as a conventional oncolytic virus, which eventually bring us to the systemic anti-tumor efficacy. So that is the concept. So in the in vitro experiment, in EGFR positive cancer cell A529, PP complex shows most potent EGFR specific transduction efficiency. However, non-targeted PP or naked adenovirus doesn't show very enhanced transduction efficiency. Also, the EGFR negative cancer cell MCF7 and the normal cell, the PPE doesn't show the transduction efficiency, which means it has the EGFR specific transduction efficiency. We have also conducted anti-tumor efficacy test of oncolytic adenovirus with PPE. As you can see here, oncolytic virus complex with the PPE shows most potent anti-tumor efficacy. In day 28, it shows 77-fold higher or 6.3 higher anti-tumor efficacy than the naked adenovirus or PP complex adenovirus. As I mentioned previously, virus is very immunogenic, so the blood retention time can be reduced. So we want to check the PP coating can enhance the blood circulation time. So we are assess the PK profile. As you can see here, the naked adenovirus rapidly cleared in the bloodstream. However, PP or the PP complex oncolytic adenovirus still retain in the bloodstream up to 300-fold higher value until 24 hours. So which means the PP polymer coating can successfully protect the virus from the blood clearance. We have also checked the BD, the blood biodistribution of the oncolytic adenovirus. As you can see here, the naked oncolytic virus, 90% of oncolytic virus goes to the liver. However, the PP complex oncolytic virus significantly, the non-specific liver targeting is significantly reduced up to 1 times 10 to 5-fold. However, the tumor-specific accumulation of virus is significantly increased up to 3 times 10 to 4-fold. More importantly, the tumor to liver ratio, which stands for the therapeutic efficacy and the safety profile, it has been increased up to 10 to 9-fold in the PP complex oncolytic adenovirus compared with the naked adenovirus, which means the PP complex oncolytic virus is very safe and it has therapeutic potentials. So today I have shown you the only one study, but we have been working with many kinds of systemic delivery tool with the oncolytic adenovirus. So we have exploring the targeting moiety, many kinds of targeting moiety and the nanoparticle, and the way to link the virus to the polymer. So the first question can be like which nanoparticle design would be the best to achieve the best therapeutic outcome. Importantly, for the virus to reach to the tumor target tumor tissue, it should endure the shear stress in the bloodstream. So I believe the chemical conjugation is much better than the electrostatic interaction, but so we can also explore that in our project group. And we have also utilized the mesenchymal stem cell as a cell carrier for the oncolytic adenovirus due to its low immunogenicity and the tumor tropism. And the MSC can protect the virus. It can be a Trojan horse of oncolytic virus, and it can also be the viral replication factory until it reaches to the tumor site. So the question to determine the use of a nanoparticle or the cell carrier for more effective delivery of oncolytic virus to the target site going to be the second questions. So even though we are using different tumor model, we have data showing the therapeutic efficacy of oncolytic adenovirus complex with the nanoparticle. When it is administered intratumorally or systemically. So the third question can be how we can compare and optimize the intratumoral injection versus the systemic injection of oncolytic virus in the two different tumor type. Yeah, the third part, the second part is the combination of oncolytic virus with the immune checkpoint inhibitor. To strengthen the therapeutic efficacy of oncolytic virus, we can use the multiple therapeutic gene in one vector system. The therapeutic gene group 1 include IL-12 and GM-CSF and so on, which can enhance the anti-tumor efficacy. And the group 2 can include the relaxin and decorin, which can degrade the extracellular matrix in the tissue so that it can improve the tumor penetration of oncolytic virus. And we can also use the short hairpin RNA against the VEGF or the thymidine kinase for inhibiting the angiogenesis and proliferation of cancer cells. So I have the list of oncolytic virus which arm 2 or the 3 kinds of therapeutic gene at the same time. And I have also data to combining these oncolytic adenovirus with the ICI. So the question can be how to optimize the possible combination of therapeutic genes and enhancing the therapeutic efficacy of immunotherapeutics. So time is running out, so I will just skip the data that I have prepared. And another question can be, we can specify the virus and predict the impact of the virus to overcome the highly demoplastic and immunodeserted phenotype of tumor. So that is going to be question number 5. So I have all the data with this. So yeah, that's it. So I hope we can have, you can have the idea to develop the model with my presentation. Thank you so much.
Thank you so much. All right, I guess in the